Hello guys, good day. How are you doing? It's been a while. I actually posted on this platform. I welcome you back once again. So by God's grace, today we shall unravel the aspect of physics that has to do with kinematics. Okay, the aspect of physics that has to do with kinematics, and kinematics is actually a branch of science that deals with motion. Okay, so the branch of science that deal with motion, that is kinematics. So today we shall, by God's grace, look at the linear motion and the necessary calculations that has to do with linear motion. But meanwhile, before we explain those calculations that has to do with linear motion, we would first look at some terms we use in describing motion. So we have some terminologies that we normally use in brief, together with the equation necessary that we use in describing linear motion. So the first term that we normally use is speed. Okay, we use speed. And what is speed? Speed is the rate of change of distance. The rate of change of distance is a scalar quantity that has the unit of meters per seconds. So which means by calculation, so we can say speed is equal to distance divided by time taken. That's just an ordinary speed now. Okay, I didn't say average speed, but just speed in its simple term, and its unit is meters per seconds. It can also be written in the index form ms raised to power minus 1. So this is the unit for speed, and it has the formula distance all over time. So we also mentioned that it is a scalar quantity, which means it has magnitude but no direction, to be precise. Okay, so that is the first terminology we use in describing linear motion. Now the second terminology is velocity. Okay, velocity. And what is meant by velocity? So when we say velocity, so what is velocity? It is actually the rate of change of displacement with time. Okay, it is dimensionally the same as speed. They have the same SI unit, but their formula of calculation varies. So we can say velocity with the symbol v is equal to the change in the displacement, changing displacement divided by time. Okay, divided by time. So changing the position of an object divided by time. So using symbol, we can represent this as saying velocity v is equal to displacement, change in displacement, x minus x naught. So which is the initial and the final position or displacement all over the time represented as t. Okay, so this we can use to unravel velocity. But meanwhile, when it has to do with the velocity of an object at an instant of time, so we call that instantaneous, instantaneous velocity. Instantaneous velocity. So when it has to do with an instant of time. So instantaneous velocity, v, putting a bar on it, will be written as change in s, that is change in displacement, all over the change in time. Okay, all over the change in time. If we go further more in our physics, we can take limit of change in t to be equal to 0. So we can define velocity as changing speed all over changing time. So velocity is a vector quantity, so which means it has magnitude, and at the same time it has direction to be specified. So velocity, it has magnitude, and it has time to be, it has direction to be specified. So we can define it as change as well in displacement all over time. Now you talk about the differentiation, okay, all over time, that is differentiation of the displacement. When you differentiate displacement. So now the third terminology we normally use when expressing linear motion is acceleration, okay, which is defined as the rate of change of velocity. Okay, so acceleration is the rate of change of velocity, that is the change in velocity all over the change in time. Basically, that is the formula for acceleration: change in velocity all over change in time. T is time. This V here is velocity, and A is acceleration. Acceleration is also, a vector quantity and has the SI unit, which is meters per second square, which can also be written in the index form as ms raised to the power of -2. Since this is meters per second divided by seconds, velocity is meters per seconds, then divide by time, which is seconds. The seconds go up, it becomes ms raised to power -1 and another -1, which is now ms to the power of -2, and which is the unit for acceleration. All right, so for instantaneous acceleration as well, for instantaneous acceleration, A bar, we have change in velocity all over change in time at an instant of time. Okay, so for this we can take limit of time to be equal to 0 in the further physics. So acceleration, we can also say, is the differential form of the velocity, that is change in velocity dv all over the t. So it depends on the nature of of the question. So we would also unravel a lot of questions in due course. So this equation you can use to unravel or solve questions that has to do with acceleration. So these are some of the equations that we use when we describe being linear motion under kinematics. Okay, so now we quickly move to the part that has to do with equation of uniform accelerated motion. Equations of uniform equations rather of uniform accelerated motion. Equation of uniform accelerated motion. So now what do we have here? If we want to derive some of the equation of uniform accelerated motion, but we have to recall that acceleration is equal to change in velocity, which is the final minus the initial velocity with time. With time, yeah. So the V here happens to be the final velocity, and then the U happens to be the initial velocity. Okay, so T is time, no doubt about that. This is measured in meters per second, and this is in seconds. So now, when we rearrange this equation, on rearranging, okay, or cross multiply, we will have that V minus U equal to A multiplied by T, AT, such that, so when we make V as a subject, so we can easily have that V is equal to, U is coming to this side, it becomes plus U plus A, AT. So this is the first equation that you need to know as a student of physics about linear motion. Okay, an equation of uniform, accelerated motion linearly. So that we have that. Now, similarly, excuse me, please. Now we should also remember where we define speed. Here we said speed is the rate of change of distance. That is, speed is equal to distance all over time. So we can rearrange this equation to make to make distance the subject, such that distance will therefore be equal to speed multiplied by time when we arrange the first equation written there. So we have this, okay, and speed is the speed here, that's the average speed. So we're going to write the speed as average speed, so that distance will be equal to the average speed multiplied by time. All right, now by average speeds, so we mean the final speed and the initial speed. We have two speeds, the final and the initial, okay? Then their average, you divide by 2. The sum divided by the total. So by average speed, we're going to write that as the two speeds are the final speed, V, plus U, then all over 2. That is what is meant by, the average. So this is average speed, this for this. So we can now write our equation. The symbol for distance is S, equal to average speed. We will write that as this, V plus U divided by 2. Then we put that in bracket, multiply by time. we have time in here. Okay, so you have your t. But meanwhile, because this equation has no what's it called, acceleration in it, so it's not regarded as part of the equation of uniform accelerated motion. Well, it could be very, very useful. It will be very, very useful under motion, because from here we can use this equation to unravel or create a lot of equations. So now from here we have that we know that v, we have derived that v is equal to u plus at. Okay, from this equation here in red, v equal to u plus at. So we can now substitute for v equal to this in this prominent equation. So we can now write that s, that is, the speed or displacement, the displacement rather, or distance, is equal to v. Instead of writing this v, we substitute it with this. That is u plus at. All right, then plus u divided by 2, and then into the bracket of t, this t, you bring it down. All right, so now from here we have t and another t, u and another u. So that's going to be s equal to 2u, that is this plus this, then plus at all over 2, okay, into the bracket of t, all right. So now from here we can multiply what we have in the bracket with the t outside, so that s will be equal to 2ut, this multiplied by this, then you bring down the plus at square, then all over 2. So now you can turn this to a different fraction, that is 2ut taking its own part of the 2 all over 2, then plus at square all over 2. So these two can easily cancel out this cancel out these two. So what do we have left? We have s, which is the displacement or distance, equal to ut plus at squared all over 2. So this can simply be written as s equal to ut plus, this is 1 over 2, okay, 1 over 2 at squared. Okay, so this equation is also a very prominent equation of a linear accelerated motion. So it is the third one that is very essential. This happens to be the third one. So I take this for the second one, though it does not have acceleration in it, so it's not regarded as an equation of linear motion, but it's very essential. Okay, and this is the first equation of linear motion that we have. All right, so there is one more that we need to get, that we need to derive. So how do we get that? How do we write that? So now we also going to get that from the equation that says the distance is equal to the average speed multiplied by time. Distance has the symbol s and average speed is v plus u all over all over 2 rather, then multiply by t, multiply by time. A very prominent equation. Okay, so now from here, from this equation where we said acceleration is equal to change in velocity all over time, that is the final minus the initial velocity all over time. Now here we can make A the subject, we can make T the subject such that AT, when we cross multiply or rearrange, will be equal to V minus U. So now T therefore will be equal to, when we divide both sides by A, T will be equal to V minus U all over A. Alright, so we have T to be equal to this. We can substitute this T equal to this in this prominent equation such that S, which is equal to the average speed, V plus U all over 2 multiplied by T. So instead of writing T now, instead of writing down this T, we will substitute it with this, which is V minus U all over A. Okay, so we multiply this with this. We'll remove the brackets now. Okay, we remove the bracket. So when we do that, what do we get? We can now remove the bracket. You multiply the numerator by the numerator, the denominator by the denominator. V multiply by V, that is V squared. Then V multiply by minus U, that is minus, VU. Then plus U multiply by V, that is plus VU. Then plus U multiplied by minus U, that is minus, plus times minus is minus, that is minus U square. Then all over, we've done the numerator, then you divide by the denominator 2, multiply by A, that is 2A. Alright, so this is minus VU plus VU. So like saying minus 1 plus 1, that will be 0, so they cancel out. So this plus minus VU is going to cancel out plus VU. So what you will have left is going to be V square. Okay, this and these are out. Then you have minus U square all over, 2A. So when we rearrange this equation, we will have that V square minus U square equal to 2AS. Okay, equal to 2AS. So when we make this the subject, so we can easily get that our V square is equal to, so minus U square is coming here, it becomes plus U square, okay, plus 2AS. So this is another equation of a uniformly accelerated motion, a very prominent one. So now we have derived all the equation of uniform accelerated motion. So the first one to rewrite is V equals U plus AT. And then the second one is V S equal to, okay, let me write the second one as this. So we have the second one as V square equals U square plus 2AS. And then we have the third one, which is S equal to UT plus half at squared. All right. Then we have all these are equation of uniform accelerated motion because they all have acceleration, okay, and also acceleration. They all have acceleration. So this one is also the last one here, which is the fourth one, is also an equation of uniform motion, but not accelerated because it has no acceleration in it, but we can use it to unravel questions. Okay, so all these four equations are what you need to know to calculate equation of uniform accelerated motion. Now we want to define the terms. What does V stands for in the equation? So this V is equal to the final velocity, okay, and the unit is meters per second, or simply written as this. Then also we have U, that is the initial velocity. I call it acceleration velocity, final velocity, initial velocity, also in meters per seconds. Then we have A to be acceleration. Okay, acceleration is meters per second squared. That's the unit. ms to the power of -2. Then s is the displacement or distance. Okay, in meters. What do we have there? Again, we have t. T is the time taken, and the unit is seconds. Okay, so now, when a body, you have to note this. When a body starts from rest, okay, important notice now. When a body starts from the rest or accelerates uniformly from rest, so initial velocity U is always equal to 0. Important notice. When a body starts from rest or accelerates uniformly from rest, so initial velocity is always 0. When an object is brought to rest, okay, when an object is brought to rest or to an halt, so the final velocity will always be 0. Very important there to note. When an object is brought to rest, the final velocity is always equal to 0. Okay, in the question, you will not be told that U is 0 or V is 0. No, you just have to note that in the sentence or the statement, when it is brought to rest, final velocity will be 0. When it starts from rest, U will be 0. That's the initial velocity. And also, when an object, is in a constant speed or constant velocity, then the acceleration is going to be 0. All right. So those are the important points you need to know respect to this point.